All right, so this is me going over your pedigree practice worksheet, just going through them the way that I would solve the problems. So starting at number 1, given the following genotypes, describe the phenotypes, normal or albino. This should be relatively easy review, right? So our homozygous dominant is going to be normal because when we read through our description, albino is a recessive trait. So we know that if you have two dominant alleles, then you're normal. Similarly, if you're a heterozygote, the dominant trait is going to take over, so we're normal. But if you're homozygous recessive, then you are albino. Then we move into actually using our understanding of pedigrees, right? So squares are boys, circles are girls, and if they're shaded, then they have the trait that you're tracking. In this case, shaded means albino, which means that for every shaded square or circle, we know that their genotype has to be homozygous recessive because they have to be homozygous recessive in order to be albino. So we know right away that our shaded shapes are homozygous recessive, two little a's. That then gives us the information that we need to figure out some other things, because here we have an offspring daughter who is homozygous recessive, and she is the offspring of this homozygous recessive father and a dominant seeming mother. So we know that she got one little a from her father, and she must have gotten this other little a also from her mother. Well, her mother doesn't have albinism, so we know that she has at least one dominant a. But in order to be able to pass on that little a and have a daughter who is albino, she would have to be heterozygous. She has to have a little a to give. So that in turn is going to give us some information about the other daughters who are normal. We know they have at least one big A because they don't have the albinism trait. So they must have at least one normal gene. And if we look at their parents, where could they have gotten that big A from? Well, there's only one option. They could only get that big A from their mother. So that's the big A that could be passed on to those individuals. Which means, because we know, according to Mendel's law of segregation, that each parent only passes on one allele for each trait, that the other allele that they got had to come from their father, and their father only has little a's to give. So we know that they're going to also be heterozygotes for that albinism trait because they had to get one from their father and one from their mother. We know they got the big A from their mother. So then to answer just some general pedigree questions, how many children does this family have? Well, there are 3 children here because we see 3 individuals coming off of our married couple. And what are the sexes? Well, they're all girls because they're all circles. So that completes that square. So now we move on to the box here labeled number 7, just sort of the next box over. And again, we're going to try to fill out all of the genotypes of the individuals in this pedigree. The easiest place to start is with the shaded individuals. Those shaded individuals we know have the trait, and in this case we know it's a recessive trait. So we know that they are going to be homozygous recessive. So we can go through, and for all the ones that are shaded, we can put in that they are homozygous recessive. And then from there, we can work backwards. Now, remember, we talked about in our discussion yesterday that anytime we see 2 individuals who don't show the trait having an offspring that does have the trait, that's a good sign that it's a recessive trait. Because the only way that you can have a hidden trait is if you have 2 heterozygotes, right, where you have 2 traits that aren't being expressed that can then come together and create an offspring who has that trait. So we have 2 cases of that here, where there are 2 sets of parents who each have an offspring that has the trait, so we know they must be heterozygous. Another way that we can look at that is by looking at them. We know that they don't have albinism, so we know they have at least one dominant A. And when we look at their offsprings, when we move down here to look at the offspring, those 2 circles and a square, we know that at least one individual, in this case a square, a boy, got one recessive allele from each parent, which tells us that they, in addition to their dominant allele, they had to have a recessive allele to give as well. And each of them had to do that for one of their offspring to come out homozygous recessive. And we see the same thing up here. So then we get down to our last circles. And in these places, sometimes we can't tell what the individual's genotype is. For example, for this circle here, which is the daughter of these two heterozygotes, there are two possibilities. We know she has at least one dominant A, but she could have two dominant A's because she could have gotten one dominant A from each parent. And those could have gone on to cause her to be homozygous dominant. Or she could have gotten one dominant A from one parent and one recessive A from another parent. Either way, she wouldn't have albinism, and so it would be impossible for us to tell. So we actually don't know the genotype for this individual. We know she's dominant, so we know her phenotype, but we don't know if she's homozygous dominant or heterozygous. For this individual over here, right, we have more information because we have information about offspring. So we know that this daughter married a man without albinism, and that they had a child, in this case a daughter, with albinism. And so we know that she doesn't have, she's not albino because she's not shaded in. So we know she has a big A. And because she has a daughter who has two little a's, we know one of those little a's came from the father. And so the other little a, again, because of Mendel's law of independent assortment, or actually rather of segregation, had to come from the mother. So we know that the mother had to also be able to give a little a. So in this case, we now know that this individual is heterozygous. We can only tell that second allele because of her daughter here, who is homozygous recessive. If we didn't have that information, it would be like this daughter over here, where we know that she's normal, she doesn't have albinism, but we don't know whether she's homozygous dominant or heterozygous. But we can go through and answer the questions number 8 and number 9. How many children does the original couple have? Well, our original couple is this first couple up here. Sometimes these charts are actually organized in such a way, in levels, so that you can sort of refer. So you'd have like 1, 2, then 1, 2, 3, sort of in generations. So you can refer to them as like the first generation, first child, or the second generation. And so you could write that like the second generation, third child would refer to this kid here. Anyway, that's just sort of a side note. So our original couple is right here. How many children did they have? Well, we look at their offspring, and they had one circle, which is a daughter, and one square, which is a son. So they had 2. And then we look at their grandchildren. Well, it looks like only one of their offspring reproduced. And so if we look at that and trace that down, it looks like they had 3 grandchildren from that one offspring, that one son. And so 3 grandchildren that we can tell from this pedigree. This child here would be a great-grandchild, so would not count in the grandchildren because that is the child of a grandchild, so that would be the great-grandchild. So moving on to the rest, again, we're going to start this pedigree the same way we started all of the others. We're going to start with the shaded shapes because those are the ones we know are homozygous recessive. And so we're going to say, all right, well, this woman here was homozygous recessive, this woman was homozygous recessive, and this man or boy, whichever, we have no knowledge of the age, is homozygous recessive. From there, we can sort of figure out some of the phenotypes. If this individual is homozygous recessive, that means it got a little a from each of its parents. He got a little a from each of his parents. But neither of those parents are albino, which means they must have a dominant allele as well. So we know that they are heterozygous. Similarly, we know that this individual over here, this girl, got a lowercase a from her mom. And we know that she also must have gotten a lowercase a from her dad, which means there is a lowercase a there. And if we look at her dad, he's not albino, so he must have a capital A, so he must be a heterozygote. And then that just leaves us with one son here in the middle. Well, we know he got a capital A from his dad because he is not albino. And that is the one that his dad gave him, which means he couldn't have gotten anything else from his dad. And his mom only has really one thing to give. She can only give little a's. So we know that he's heterozygous from that. Then we go through and answer our questions. How many children does the original couple have? Well, in this case, there's one circle and 2 squares. So that is 3 children. And how many grandchildren does the original couple have? Well, the next question sort of answers that for us. But if we see only one of this second generation is married and has any offspring, so we only have to look at the one place where there might be grandchildren. And in this case, there's only one grandchild, so that's 1. And what sex? Well, it's a square, so it's a boy. It's male. And that completes that question. And as we move on to the final question here, this one is now about rats, male and female rats, and their pedigrees can be a lot harder to figure out because they reproduce a lot more, but we're going to follow the exact same method. So we're going to go through and say, well, all the shaded ones are albino, which means they have to be homozygous recessive because albinism is a recessive trait. So we'll start with May, then we'll go with all of the offspring that are homozygous recessive that are shaded in. So we can go through and fill in all of the shaded ones with homozygous recessive. Now this depends, how you approach this depends on what trait it is that you are tracing. If you're tracing a dominant trait, you wouldn't necessarily know that all the shaded ones were homozygous recessive, but you would know that all the not shaded ones were homozygous recessive. So the way that you approach it just depends on what trait it is that you're looking at. Well, that suddenly cleared a lot of things up. We have a lot of individuals who are homozygous recessive, a lot of albino individuals. And so now we sort of build from there and see what we can tell. I sort of like to start at one end and just see what that tells me. So for example, here I have, so I'm just going to start at the bottom. I have 2 individuals who were homozygous recessive, who were born from 2 not albino parents. So we know that these parents are not albino. We know that they have at least one big A. Given that they have some albino offspring, that means that each of these offspring got a little a from both of their parents. So this parent has to have a little a and this parent has to have a little a. So both of them have to be heterozygous. As far as their offspring go who are normal, they don't have any offspring that we can use to tell. We know they have one big A because they are not albino, but because they're the offspring of 2 heterozygotes, they could be either A, big A, big A, big A, big A, or big A, little a, big A, little a. We don't know. So these are ambiguous. There's no way for us to tell whether they're homozygous or heterozygous. So we have to be careful about not assuming too much information. And then from that group, I would move on to, let's say, this group here, where we have 3 individuals already filled in from the pairing of Manny and June. We know that this individual is a female rat, and we know she has at least one big A because she's not albino. But if we look at her parents, we know that one of her parents was albino, which means from that parent she could only get a little a. And so we know that this individual is going to be heterozygous then, and she must have gotten the big A from Manny. Right? And so Manny has a big A. We know that. And if we look at some of Manny's offspring, so let's look at his offspring here with May. They have some offspring that are albino, that are homozygous recessive. Well, we know they got one A from May because May is homozygous recessive, so she gave one little A. But in order to get that second little a, it had to have come from Manny, so Manny must be heterozygous. That means that this offspring here, this daughter rat, got a big A that must have come from Manny because it's the only big A in this mating couple. And so she had to have gotten a little a from May, which means that individual is heterozygous. Then as we sort of come over here to where Manny and April have offspring, just sort of moving counterclockwise now. We know that these individuals each have a big A because they are not albino, so they must have a normal hair color gene. And we know that they're also